All right, so we're here in the second lesson of our load model, or load module. We're going to focus a lot on initially here about some process related things and some background kinds of information. When you're taking 4900 next fall or next spring, one of the two, that's the capstone design sequence, you're going to be really interested in these kinds of things that you see here because you're going to have to answer some open-ended questions. One of the most important things you do, no matter whether it's structures or any other subdiscipline, is you got to figure out what's the basis of design. And part of that basis of design is understanding how do I go about meeting my ethical requirement of protecting the health, safety, and welfare of the public and of the environment. And one of the answers is, oh, we have these things called building codes, and but you got to figure out which one is applicable in that particular situation. And that is not a no-brainer. Everybody knows it's just a building code. No, that's not the way it works at all, because every jurisdictional authority has the opportunity to specify which version and which building code that you should follow. Yeah, there's more than one of these things that are running around. Whether it's a federal facility, whether it's a state government facility, whether it's a private facility, all of that could potentially change what your criteria are that you're going to be using. So we're going to talk a little bit about the background of that. We're going to fly through some of this. There's an awareness thing that we're trying to create here. I've given you a lot more detail in the handout than we're going to verbalize. I just want to point out some things here so that you can then in your study go back and look at some of that in more detail. And then we'll come back to applying some of these as we on the back end of where we're at today. The big context though is an architect's come to you and they want to design a building and you're responsible for developing that structural system. And so, gee, you got to go get demands so that you can then go figure out how big the thing needs to be. Well, that is the demand. Well, okay, but what material are we using? And then what's the acceptable strength of that? All of that comes into play in these various things called codes. So that's what we're going to get into. We're going to focus today on just gravity loads. Next time, we'll start to get into lateral loads, so wind loads and earthquake type loads, lateral earth pressures. We're going to get into all that kind of thing, the structural systems that we use to support that, and including we'll talk about the earthquake that we had last spring and the big windstorm that we had last fall as well. All right, so we'll stick here just with the dead and the live loads. Let's really start with part of the big picture here. You don't just build something because you want to. Now you can get away with that in your backyard. You can decide to build a storage shed without necessarily having a building permit. That can be kind of sketchy too, depending on what kind of storage thing you're putting up there. But recognize that before you can build, there is a process that you have to follow, and this little flow chart helps you to see what that looks like in the big picture of that. And then when you have a facility that you built, you don't just get to go into it. You got to have a governmental official that's going to come in and say, yes, it's okay to be occupied. So again, there's something that has to be followed here in real world terms, and this page is laying out what some of that process is. Right now, almost everybody has heard of this notion of a building code. Few, though, who aren't in the business or who haven't gone through an engineering program know what that really means, right? And so the jurisdictional authority is typically the state, but it's not necessarily, right? Some states have multiple jurisdictions. So Northern California, Southern California, different groups that are have some authority. New York State has their overall state jurisdictional authority, but New York City has their own building code officials, and same thing in Chicago versus Illinois. Now, some of that has been unified over the last 20 or so years. It used to be in the country that we had about 4 different model building codes, and depending geographically where you were at, that would, you had to buy 4 different ones of these things. Starting in the early 90s, there was an approach to to come along and say, look, we need to try to start thinking about how we might have a unified building code across the country. And that unified building code did happen, and it's called the International Building Code. There ain't nothing international about it in reality, other than the people who made it up actually come from all over the world. But in reality, it's a US building code. But they did this, they called it the International Building Code because they wanted to sell their product to the entire world. Wait, this is engineering. What are you talking about selling a product? Well, these organizations don't just sit there and exist for altruism, right? They're not in it to make money, but they have to support the development of the code. And yeah, there are maybe some governmental resources to help support that, but that's only if they get granted money to do that. They have to apply for that kind of money. So they have to sell their product, and the more they sell, then the more that they are financially viable, right? And it's up to the jurisdictional authority to decide which building code are we going to use. Now, the federal government can kind of control that a little bit more across the country, but we have in this country state rights. And so every state has their own legislature that gets to decide which building code are you going to use for non-federal projects. And so what happens ultimately is that we engineers write things called building codes, but they're not building codes. What they are is standards and specifications that are written in legal language to make it easy for the legislative bodies to enact them, to decide that, yes, we're going to make a proposal in front of our legislative body, and we're going to go, and then everybody votes on it, et cetera, et cetera. Of course, that means that, they're not engineers. They don't know what they're voting on. So they need somebody to come in as experts to provide the insight to what that particular prospective legal code is going to mean, and why are you making changes and that sort of thing. That's typically the Board of Engineers for that jurisdiction is the one that's going to be the one testifying in front of that body, right? So that's just a little bit of the background that's going on there. The basic structure here then is that we have an actual legal code that then is adopted by municipalities, maybe with some modifications, maybe or not. Those legal codes come from the model codes. That's the International Building Code. It is written as a model, and then it gets adapted to the particular location because it is meant to be universal. There's a lot back in those 90s. There was a bunch of fighting that would happen between, heck no, we're not going to do that here in Oklahoma. We don't have earthquakes. We don't need to design it as though it's out in California, for crying out loud. And I'm actually painting that in a very gentle way. The language that's used is a lot stronger than that. This notion of, state rights across different areas of our country are very strong. It's not, I used Oklahoma because I used to live there. That's where I lived before I came to Utah. Before that, I lived in Indiana. Before that, in Kentucky, and I was in California for a while. So I've been in Pennsylvania. Just all over the place, right? And the independent streak that we have in this country is a very strong one. And so we don't, we are very careful about trying to design things in ways that make sense for our particular location or for the location of the project, and using things that don't unnecessarily drive up the costs, because we're supposed to protect the public's health, safety, and welfare, but also of the environment. And we also have the ethical requirement to protect our client as well, right? So don't unnecessarily spend money. Don't drive up cost and create a Cadillac, Lexus, BMW, Mercedes of a building when a lower cost model will do the job as well, right? So we've got these building codes, and those building codes are going to refer oftentimes to standards. Think of standards as sort of the technical academic document. And they'll also be written in terms of legal standards or legal language, but they are in a sense, sort of the real truth, but they're not necessarily applied yet. And that's what the building code does, is help to apply it, right? So we've got a whole variety of model codes. You got this big general international building code that is pretty much adopted throughout all of the United States. Then we have these material specific things, because the International Building Code is going to set some high level things, and it's going to then refer to the specialist if you have a reinforced concrete building. So ACI 318 is the particular one of that. The Manual of Steel Construction will include the steel design specification, as well as a whole lot of design tables. The timber folks use the National Design Specification. Notice the name, the National Design Specification, as though there's only one for the entire nation, right? They're selling timber, right? The AWC, the American Wood Council, is trying to promote wood products, and part of promoting that is providing the standard by which you would then design wood-based structures. And so they call theirs the National Design Specification. That dates historically before we had the International Building Code. We had the Southern Building Code, we had the Uniform Building Code, you had BOCA, I forget what that stands for, on and it went. There's one for masonry structures, et cetera, et cetera. I mean, this goes on and on and on with various organizations. And if you want to go into full-time practice, you have to have all of this stuff. And they change from year to year, which is also a bit of a pain. All that stuff that was on that previous page, that was just for the strength side of thing and a little bit on the loading side. But the standard for loads, if you're doing buildings and other structures, is ASCE 7. That's the primary one, right? But that's for buildings and other structures. That's not for bridges. If you want to do a bridge, you now got to deal with AASHTO, and you got to deal with the DOT of that particular state, and they'll have a whole series of standards. So our structural profession gets broken into two different disciplinary areas. Bridges are entirely their own business market, and everything else is sitting there somewhere else. And even though there's towers, there's pipelines, there's all kinds of other structures, they all get sort of lumped somewhere else. Railroads, they're their whole own little deal as well. But bridges in their funding come typically from public sources. We don't have so many private bridges. So that's a big reason why they are split off and into their own little group. And so we're only showing you things associated with buildings and other structures here. And so you see a variety of other ones. The big one that you need if you have a federal building is the Unified Facilities Criteria. So that's not just Department of Defense or military related ones. That's any federal owned or leased space would fall under the Unified Facilities Criteria, right? I know this is not the most exciting stuff in the world, is it? But wow, if you don't have the appropriate standard that you're going to use, you're nowhere. So this big one that will cost you about $250 to $300 is ASCE 7. The International Building Code will refer directly to ASCE 7. The sort of the most recent one is 2016. It used to be that this was updated every 3 years. For the last 20 years, they've been trying to change the renewal cycle from about 3 years to about 5 years. And because it costs a lot of money to go through all this process. This ASCE 7 is regarded as a standard, and as you see here in the bullet, it's just typical situations only, which is typical of all of our building code requirements. They try to do the typical garden variety situations, and it's our particular American approach to how we handle design, at least in the civil structural side of the world. Special situations then leave you a little bit more room for your professional judgment than, say, the garden variety type of situation, right? In all of this, notice that a key word, minimum load requirement, right? Your professional responsibility is not to do the minimum, it's to do what is needed. But these are the minimums that you need to be looking at, not the maximums. Right, so that's another big thing that goes on. All right, so a lot of verbiage here, blah, 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 blah. There's a lot more detail here. Let's just hit a highlight. And that is that at some level, you're trying to come up with a reasonable maximum amount of load to apply to your structural model. Your guide is this minimum design load standard that gets referred to in IBC. So by the way, you got to pay something like $250 just for one portion of the International Building Code. It goes vastly beyond just structures. It deals with mechanical stuff, electrical stuff, lighting stuff. It goes on and on and on. And it's a lot of money if you want all the volumes. The architects need to have all of those. Us, we particularly need to have just one particular part of all that. I think it's chapter 16. But that ultimately sets a bigger backdrop for minimum loads that ultimately just broadens and refines ASCE 7. So you got to buy both. So now you're into this for $500. Oh, by the way, all those other design standards that were on the other page, they're going to be anywhere from 150 to 250 a pop just for those too. Good stuff, huh? A lot of money is going to come out of your budget just for keeping those up. Right, so every 3 years, the next one actually for ASCE 7, for some reason they missed the 2019 cycle, and the next one will be 2022 for ASCE 7. Right, that has to get done before then you produce the next IBC. So there's always this staggered kind of thing going on in terms of the dates. And you'll often find that, especially a small municipality, they won't be using anywhere close to the most recent version. They may be 10 years behind, which may or may not be an important thing. It just depends on what happened in the last 10 years of the changes that were made in the building code. For ASCE 7, the way we look at loads are to classify them by environment, right, and source of the load. So there's a whole laundry list. This is reasonably comprehensive. It turns out that they've now even broadened this a little bit. But notice that we've got the dead load, and the symbol that we use there is for D. Because of the nature of ICE, then we actually separate out that particular dead load as its own little special thing, right? You've got E for earthquake because S is already taken up with snow, right? And so on and so forth. I'm not going to go through all of them. I just want to point out two more. We've got those temporary gravity loads, the live loads, but we separate out them from live on the floor versus live on the roof. And that's because the nature of those temporary loads are so different that we don't want to lump it all together. And you're going to see this not in this week. You're not going to see it I don't even think next week it's going to be in lesson 5, where we'll do the official load combinations, where that distinction turns out to be truly important in how we do that combination of things. So for right now, it's going to seem like I don't get it. I mean, I'm just going to go to different locations and get the values. Why do I have to call them different, something different? And that will be coming up later on, right? So, and we're not going to go through these details at all, but you've got them. They're in very small print, and they're expensive, right? You're getting a little bit of a free version. You could even begin to argue that we might have even strayed a little bit over the line here in what we've provided. There are copyrights on these, and there's an argument that's made between academic privilege to be able to copy some of this, and it's an interesting challenge, and people who will vigorously debate on either side what you're allowed to do. I've taken kind of a middle road, but it's a little bit of an aggressive middle road in these particular tables. The thing is, these tables, especially the design dead load tables, you could find anywhere. So there's nothing really being given away here. And you'll find a lot more detail, not especially nicely formatted, but a lot of detail here, that much more that you have in your textbook, right? And you'll see here's your deck, metal deck 20 gauge, metal deck 18 gauge. Those aren't the only thicknesses that are available, but those are the two most common, right? And you got a little bit more wood decking kinds of things. That's not plywood, right? So you got to be really careful here Note, we do have a plywood section that's per 1/8 inch thickness, right? And you don't buy plywood in 1/8 inch, right? 1/4 inch is about the thinnest you're going to get, but there's 3/8 inch, there's 1/2 inch, there's 3/4 inch, there's inch, I think there's 7/8. I think they come in basically 1/8 inch increments, but at some point, as they get thicker and thicker, you start to lose the resolution there. And they actually do vary quite a bit, depends on how dry they are, you know, et cetera, et cetera. So there's something about the nature of where these numbers come from. In other words, you pick up any of these components and you actually do the calculation on how much it weighs, it won't be exactly this number, right? There's something else going on probabilistically, and we'll talk about that not next week, but the week following, right? So lots of detail in here, and you gotta patiently go through all this to figure out what you want, right? Wow, there's another whole page, right? Note, table C 3.1-1A, right? When you pull values out, you've got to document exactly where you're pulling it out from, right? So that will save you some fist fights in the office about why you've chosen one number over another. You can say, oh, you took it from there. Oh, well, in this office, we tend to use this other table. And so then they'll teach you up on what they tend to do, right? So et cetera, blah, 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 a lot of stuff in here, right? And then we finally get to this next page, and now you have the live loads. These are floor live loads, right? So they're both area loads and they're minimum concentrated live loads. So now, whoa, what? So we've been dealing and talking about area loads, but you have dual, actually it's more than dual because that suggests two, but we have multiple level of criteria that you have to deal with. One of it is to spread an area load out. Say this 50 refers up here, pounds per square foot, in parentheses is the equivalent number to use if you're in the metric system, right? That's not 50 times 2.4, it's 50 or 2.4, right? And there are units associated with it. So you're supposed to spread out the live load in appropriate locations, and that would be all over the place, 50 pounds per square foot. But you also have to look potentially at a single concentrated load, in this case, for that occupancy out here at the right of the 2,000 pounds. That's a single concentrated, and you got to move that to where it creates the worst effect, right? Kind of a pain, right? I mean, you got a lot of analysis you have to kind of deal with, right? And so these are based upon different occupancy or usages of that particular area. So on any one floor, you have different areas, and you got to go and change the live loads depending on what's going on, right? Now, access floor system is a raised floor system and in a computer area. And so, at least typically, right? Either sometimes in offices, but oftentimes in where you have a whole bunch of computers set up. And that's because you have a whole bunch of equipment, electrical and ventilation, that you're throwing underneath the floor. That's above the, say, floor slab. And so that's what's going on here and why that's a little bit heavier that they're dealing with, right? You got some assembly areas. Those assembly areas may depend upon, well, they certainly depend on the kind of facility that you have. So we separate out stadiums as compared to fixed seats of lobbies. Oh, wait a minute, holy cow. So if we're talking about a lobby compared to an office space on the first floor, I got different live loads, you betcha, and you got to change it all. And these tables are giving you that kind of thing that's happening, right? And you know, the numbers are generally, these live load pressures are generally between, say, 40 PSF and up to 150 PSF. Stack rooms and libraries are pretty heavy. That's not a movable stack necessarily. So that could, we may not have that category in here, and now we got to deal with that. But, you know, look at the libraries, reading rooms, stack rooms, corridors above first floor. So not all corridors are equal either. Here's your office buildings. This category is one of the ones that you'll use the most frequently. You get special live loads like a manufacturing system, and you get 250 pounds per square foot. So your more typical ones between 40 and 150, but you do get heavier ones in terms of pounds per square foot that you might be dealing with. When I did my pre-sale condition assessments for you might call them high rises, they're not, they're mid rises, a 16-story building, that sort of thing. What you would go do is you'd go in and look at some of these spaces that were renting out to law offices, law firms, and you would look to see in the floor system, did they do anything to accommodate the heavy loads that oftentimes are in law offices. They have these movable stacks of all these documents, and those get up to around 150, sometimes even 200 pounds per square foot for a live load. And you want to make sure that that floor system has been designed to handle it, because your typical office space would be 50 pounds per square foot. And I'm telling you, baby, those law offices will have storage all over the place. What's supposed to be a corridor will have a little 3-drawer horizontal file cabinet stacked out in that hallway. It would be fun to go through these and, maybe send a little note to OSHA and say, hey, go check out this law office, see if they've actually have the space for ingress egress that they're required to have. You don't really want to do that, right? But it points out that people that use spaces are going to do things they're not really supposed to do. And as designers, we have to kind of think about that a little bit as we go about. We don't want to over design, but on the other hand, we got to protect about what's the likely usage of the space. And law offices are one that they just have a lot of documents they got to deal with, even in this day and age of digital stuff. And actually, what we have observed in the last 30 years is that digital storage has not done anything to decrease the amount of usage of paper. It's only actually increased it. And we have an additional problem that with all this computer storage, you now have floors and buildings that are dedicated to racks of computer equipment. That's heavy loads, both from the standpoint of the physical weight, but also from the standpoint of heavy loads on heating, ventilating, and air conditioning, which means now we got to have bigger units for that. And so now we got big loads that we have to deal with from a physical standpoint, as well as the loading on the building from a atmospheric or environmental kind of perspective, right? So let's get into finally a numerical problem. And this one is actually very similar to one that's in the textbook. You don't have the drawing of the building, so I'm going to sketch one out. We're going to switch over here from this to my document camera. As we do that, I want to ask you if you got any questions you want to ask before we charge off. I know that was all pretty dry, right? I get that. I've got like 15 people with the courage to leave their cameras on to show that they're engaged, and I've got about 15 people who say, I'm sleeping. What? Nothing? All right, somebody turned on their, right, please turn on your cameras, is what I'm asking you to do there. All right, so let's flop over here and do a quick check. Is this zoomed in enough? You want more? We're okay. Well, I'm going to zoom in just a little bit anyway. All right, so we are out there now on page 23, and this is the one that we're going to be working with. It you're going to see in the buildup of these problems something that is classic with this author, and that is, yeah, the problem statements are long, but that's because he's trying to teach you about the real context of how you're going to encounter these things in practice. So he's given you a lot more information than you could say you really need. And that's because our goal is not to teach you to learn how to calculate things. Our goal is to help prepare you to become an engineer. So I'm flipping through the textbook because I want to get to the equivalent or the inspirational item that this example problem came from. And it came from page 68. There's problem 1.5, that's not the specific one, but this is typical of what I see when I am working with an architect early in the design process. They'll come and have laid out a tentative floor plan, and they're going to want to ask me something about, hey, what kind of basic structural system do you think we need to work with here? And roughly, where do you think you want to put columns? They may have a very definite idea where they want to put columns, but if it's a good architect, they will engage me early on in the process so that even though I'm not the one that's going to control cost, the constructor will do that. But I may have some pretty good ideas about what the impact is of their choices early on in the design. It costs very little early on in the design to make changes. Later in the process, it's a lot of money. So in this particular photograph you see here, if you zoom in a little bit on the with your eyes, study really closely, this column is not out at the edge of the structure. They want to create big open space that's as uninterrupted as possible for the view out of this multi-story building. And that's pretty common, right? Only us structural engineers love to see the structure in braces and all the rest of it. Everything else wants to get hidden up so you can see out. And that's what you've got, is this floor to ceiling glass without any columns out here. And so, you know, if you've got this potential space down here, early on, the architect is going to start asking me about the schematic of the structural system and how that might all flow. Right now, I have a little bit of a graphics problem here. The one that our problem is inspired from is actually 1.6, which is right down below on the page. And I can kind of sneak it in there a little bit. Maybe if I come up here, I'm going to change a whole bunch of things by moving the camera around. There we go. You can begin to see it. Again, sort of a schematic of the way the space would be used. Now, way back when I was in Cub Scouts, long time ago, right? Then I wanted to be an architect, and a local architecture firm brought us little Cub Scouts over, and they were going to take us through a series of things to teach us how to be an architect. And the first thing they taught us was bubble diagrams. This is a little bit more than a bubble diagram, but it's arranging different spaces of usage. And we got reading areas, we got stacks, we have offices, and we have all this corridor space that's all over the place. And I looked at that and I said, bubble diagrams, I'm not interested in that. I want to put dimensions on all this. And you know, I loved looking at these magazines that had these floor plans of houses typically. And I loved looking at all the details and visualizing what was going on with all that. I didn't know I was preparing myself to be a structural engineer, but that's kind of what I was really doing way back yonder. The stage to that, though, is you've got to come up with the basic essence of what's going to happen here. And you got to start thinking about, from a structural engineering standpoint, well, what are the demands that we're going to put on this floor system? And early in the process, I don't have dimensions. All I've got are some general ideas of, okay, the reading area is going to take up about that much square foot, the stacks that much, the office is that much, and the corridors such and so. And so what we're going to do is we're going to go and figure out what live load values there are here. And then we're going to try to figure out how we might work with that to come up with maybe a unified value across the entire floor space. Because one of the things that's going to happen is during the design, people are going to change their mind about what they want to have happen. But if I've already done a bunch of calculations, that can be devastating to the budget. So I'm going to try to predict something. I'm going to try to make a guess about what might work better. And then what we're going to do is also consider that over the lifetime of the building, things may change. And I want to be able to have a structural system that is not going to be too much to build to begin with, but will be able to be adaptable and flexible over the lifetime. This is where sustainability comes into things, right? I can't affect sustainability of steel. All structural steel in this country is already recycled. So telling me to use recycled steel is stupid, right? Sorry, it's stupid. It's already recycled, okay? So don't tell me to go do something that's already going to happen. That's like telling me to breathe. Great. That's the way to stay alive, is to breathe, right? So instead, what I can do though is think carefully about how I do this initial design. And so we'll just use the table 1.3 out of Hansen for our values. And when you're looking at your homework, that's what you're going to want to do. So some of you I know have access to table 1.3 in your text. Let's go look up what a reading area in a library might be for a live load. And as you're doing that, I'm going to put a little footnote there. I'm going to add that to say, okay, I'm going to take my values from Hansen, table 1.3, which in itself refers to ASCE 7. Now, there's a little bit of an argument. He says 2017. It's actually officially 7-16, although it was published in 2017. So it's crazy, I know. What do you find for a reading area in a library for a live load? Anybody?
60 PSF.
Absolutely. So got 60 PSF there. What do you find for stack areas?
It's 150 PSF.
And it's right in that same area. Now note, and this is really crucial, when you see that table, you're going to see that stack rooms has a superscript. And what you're going to find down here in the superscript is, or a footnote, live load reductions for these uses is not permitted. So what happens here is, remember, we're sort of saying that we're just going to lump all these areas or these loads, whatever's causing them, into some sort of smeared out value. So 60 pounds per square foot is for reading areas. Well, reading areas are where you have tables and chairs and people, right? And the actual load that goes to the floor are a bunch of concentrated forces from the points of the legs of the chair and of the table, if you're standing, of your feet, but you're moving around, right? And what you do is you take all that load and you just smear it all out, right? Well, 60 pounds per square foot, that means 60 pounds for every square foot. Now, let's take a 200-pound person. A typical person, especially if you're about 200 pounds, you'll be about 24 inches wide and maybe a foot, that'd be shoulder to shoulder, maybe not really 24 inches, that might be closer to 18, but between 18 and 24 inches wide from shoulder to shoulder. And from your back to your front will be about a foot of thickness. So equivalently, in terms of space on the floor, you're taking up about 2 square feet. So a typical person that weighs 200 pounds is going to be the equivalent of 200 pounds divided by 2 square foot. That's 100 pounds per square foot, right? So when you're standing right there, 100 pounds per square foot is a person. 200. Wow, wait a minute. If we had 100 pounds per square foot over the entire floor, that would be one heck of a jam party, wouldn't it? I mean, that would be everybody so close together that you could not move. Now, maybe you enjoy that environment. I don't know, don't care. But that's what it would mean, right? And that's not, of course, really that possible, except for when you have an emergency and everybody's trying to get out of there and they're jamming up against a door trying to get out. That's when you might begin to see that. And that's why corridor space will be a higher live load than, say, a reading space where you got chairs and tables and you're spreading people out. Now, stacks that are fixed to the building, right, that aren't movable stacks, well, you got big, heavy racks, multiple shelves, lots of books, lots of paper documents, and that's why that live load gets kicked up so high, is because it's 150 pounds per square foot. And that superscript, which says you can't reduce that, is relative back to this notion that, okay, wait a minute. If I'm trying to deal with a whole big wide area, the larger the area, and I'm saying people load, the likelihood that all of that space is filled with lots of people is small. And gee, if the bigger that space, even the smaller that it's all going to have that full live load. So we have this thing called live load reduction. That's as far as we're going to take it in this course, because if you never take a live load reduction, you're not going to be harming The only thing you're going to harm is the potential budget. You're not harming safety, right? You might be over designing, but at some level, over designing is better. Well, it's certainly better than under design. And so it gets a little complicated to deal with live load reduction. I just want you to know that it exists. And that's kind of the big deal there. All right, so office space.
Can I
Go
ask a
ahead.
question? When it says unfactored live loads, is that just before you account for the factor of safety?
Sort of. You're in the right area. There's a precision of language about there about factor safety versus load factor versus resistance factor. In essence, those load combinations I referred to earlier today, those will have load factors. And that's when we'll deal with moving away from unfactored. So right now it doesn't, it's additional burden for you as in terms of terms that doesn't have a context for you. That will come along in 2 weeks. Good question.
Okay.
Right, so office space, when you look down, you'll find in our table in the book, we got 3 categories: lobbies and first floor corridors, or are 100, and the office space is 50, and corridors above first floor are 80. Right, and again, that's that notion of that if I have a means of egress on the ground floor, that exit level, it's far more likely to be more packed up in that corridor than it is in above ground. And since we're at elevated floor, then we'll take the 80 PSF for that corridor value. So these would be the basic values that I would want to specify. Now, you might want to say, the architect might say, come on, give me an approximate design. I'm like, well, I need to know where these weaving areas are, and et cetera. So, well, I don't know. It's like, thanks. Can you tell me something about the approximate space that they're taking up on the floor? Well, yeah, okay, I'll tell you that. And so that's what they've done here. And so what you could do is come up with a weighted average for this to come up with a single smeared out value. Now, some people would just look at these numbers and say, all right, I see a 60, a 50, an 80, and 150. I'll just use 100. Well, okay, maybe. Other people say, why don't you just use 150 over it all? That would be way too much load. And you talk about overkill. And I would be appropriately kind of slapped, at least verbally, if I did that. So let's just look at the proportion of the areas. Let's add up all of the square footage that we've got. You do it too. And I come up with 12,200. I'd like you to double check that math here. I think that sounds about right? Because we got about 6,000 here, 3,000 there. So that's 9,000, and adding 2,000, that's 11,000. And I sort of truncated there. So I think it's probably correct, but anybody?
Yeah, that's right.
And so then what we'll do is we'll just use a weighting factor here. That is the ratio between then how much space that thing occupies. And so that's just that dividing that space by the 12,200. And rather than actually doing that number, just from manipulating this whole thing, I'm going to multiply this weighting factor times that value there, and then we'll just add it all up, right? I'm going to be dividing by the 12,200 each time. So I'm going to factor that out of the thing, right? So what I'm doing is I'm taking the sum of the load times the space divided by the total space is what I'm doing there. And so I'm going to just do it this way in terms of actually put it in my calculator. So I'm going to take 6550 times 60 plus the 3250 times 150 plus 50 times the 600 plus 1800 times the 80. It's going to be some big gigantic number, right? 615,000 divided by, or 615,750 divide by, guess what? I messed up there. I'm going to do it this way here. And I'm just adding these numbers to memory each time this time. Oh, I got a different total. Yikes. Anybody have a final answer?
86.4.
86.
Oh, yeah.
I got that as well.
Same.
Cool.
Me too.
That'll save me trying to do this live. What was your final? 86.4?
Yeah.
Right, so that might be the one that I would use to sort of hedge bets here, right? And you'll see this in the, our first charge was just to come up with this first column, and then, the principal would like us to provide advice as a way to hedge the bets for the layout changing during the design process and over time of the usage of the building. So this might be something, this level of precision is crazy, okay? And yeah, that 0.4 PSF over the whole floor area, so 0.4 times 12,200 is 4,880 pounds. Well, about 5 kips of extra load is not very much in the grand scheme of buildings, right? Maybe a one-story building, maybe a single column, but even a single column, that's nothing. So if anything, I would round this up to 87 PSF. Adding 0.6 is not adding anything particularly significant, because I know doggone well that the architect is going to lay out that approximate floor plan to the owner, and the owner's going to say, I don't want to do that. And they'll change something. And if they change it in a minor way, if I design it for 87 PSF, well, I'm golden. I don't have to redo all my work, right? Think about it. You've just done 20 pages worth of work, and somebody comes, handwritten work, and somebody comes along and changes something, and you got to redo all that. I know as a student, you're saying, heck no, this is good enough. I'm turning it in, right? As a professional, you have to do something. Well, then you might say, well, but I got it in the computer. I just changed a number. Well, that's what the architects always think. The problem is they want to change a column by one location by 1 inch. That's going to change the span length on everything. And it's not just so simple as just changing it in the structural analysis software and letting the computer do all the work. It changes everything. And if nothing else, you have to review the detail of every single little thing. It is a pain. And so what you do is you hedge your bets. There's a whole little great ditty that goes with A Few Good Men. Anybody remember what the movie A Few Good Men is all about? What the famous thing is in A Few Good Men?
You can't handle the truth.
Yeah, that's it. I can't handle the truth. That's true. I can't handle the truth. So, the whole, you can't handle the truth. I mean, it's so iconic. Personally, I don't like any of the actors in that movie, but I love the movie and their performances, even though they're actors that I don't really care for, there are amazing performances, including Jack Nicholson's performance. I claim that the highest power performance ever was Jack Nicholson's, right? His time on screen is so small, but the impact of his performance overwhelms the entire movie. And there's this whole thing, you can't handle the truth. There's a whole thing between architects and structural engineers that they've done. You over-designed that building. You're darn right I did. Because we have to. We have to in many ways because of these changes, trying to predict the changes that are going on. So I might, frankly, I probably wouldn't even do 87. I would probably throw 90 on that and hedge bets. Now I got to be careful again because, if I'm doing 3.3 PSF too much times 12,200, I'm putting now an extra 40 kips on the building. Now that's starting to catch my eye, but that's going to be spread out over the whole floor. So maybe not that big a deal. And oh, by the way, that's only the live load. That wasn't even the dead load, right? So that little additional 40 kips in the grand scheme of things, probably is not going to be a big deal. It's going to be a huge deal when you put this number into your mastering engineering. They're going to say wrong, 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 wrong. And they're not going to tell you why. So in mastering, when you're doing those, you do have to be a little nerdy and you have to be very careful. So I know, for instance, a typical mistake that's made is to not account for the thickness of the material when you look up something and forget to do that. And it might be the difference between 0.2 and 0.6 PSF in the summation of that item. Yet that will be marked wrong, right? So you do have to be careful and pay attention to that little tiny detail. That would be an error if you did it on paper too. I would catch that and say, okay, well, that's not quite as good a quality. But, you know, if on the other hand, you come along with something and say, look, I don't know if, you know, the problem statement doesn't say that this particular level is the ground floor or whether it's above ground. And it matters whether I use 80 PSF or 100 PSF. I've chosen to use 100 PSF because I've made the assumption that it's a ground floor. That's perfectly fine. You know, make that engineering judgment, but articulate what you're doing and why. Don't just write down the number and then try to argue it later. Articulate exactly how you came up with things. And I'll pay attention to that because that's what I want you to do, is to make those professional judgments. All right. So this last one is our supervisor needs a quick estimate of a live load structural model for a floor beam that supports a flat roof. The roof plan is a simple rectangular shape of 20 feet by 30 feet, corner supported with spandrel edge beams between columns. Right, so a diagram here will be helpful to try to begin to visualize what's going on. Right, we didn't actually have quick estimate of a live load structural model for a floor beam. All right, so this is kind of worded a little poorly because there's a little bit of contradiction that's going on here. But let's lay this out and try to figure out what they're trying to get at. Right, 20 foot by 30 foot. So I'll use an inch equals 10 feet. Would mean that we have a basic rectangle that has an aspect ratio of 1.5 to 1, right? 30 feet by 20 feet. Says we have corner columns. So where's my little template here? Pop a little square out for the column. I don't know if it's a two-way slab. It's some sort of reinforced concrete. And that means the columns are probably concrete. And that means the columns are either square or rectangle. So we got square columns. And then it says we have spandrel edge beams. Those would probably also be rectangular in cross-section. They could be L-shaped, an inverted L, capital L that's turned upside down. That would be pretty common for spandrel edge beams too. There's our edge beams. Now, so when they say a quick estimate of a live load structural model for a floor beam, well, wait a minute. If we don't have beams in the middle of this thing, then there's no floor beam. Well, so that's the sort of problem in the problem statement in terms of precision. They really should have said an edge beam, right? And it supports a flat roof, right? So it's a two-way floor slab, right? Two-way means that it bends in two directions. So if you take your just basic beam, here's my beam here, and you know, in mechanics of materials, you learned how to figure out how it bent, right? It's pretty thin in this case. That's one-way bending. Right, but this floor slab going over all of this is going to bend in two ways. It's going to span across that direction, and it's going to span across this direction. It's going to span in two ways, and it's going to bend in both ways. Right, and so that changes how the load is distributed. If this were one-way action, if I did not have an edge beam on these two short sides, then I would say it spans only in one direction. And this floor slab, then I'd draw a tributary line right down the middle, and it would go half of the load would go to that side, half would go to that side. But because it's supported on all four edges, or if I had no edge beams at all, then I've got this two-way action. I've got dishing or bending, that sagging that's going to happen in both directions. And that's a pretty complicated stress analysis to do. We simplify it in our design procedures, but it's an advanced graduate level course called plates. And you learn about the mechanics of all that in a plates class. And they call it a plate partially because it kind of looks like your dish plate, right? That dish plate is a saucer, and that's what the deflected shape of these things look like, is a saucer, right? So the way that we handle this, when you have a ratio that is less than 2 to 1, remember last time when we did those tributary models, there was something that said, hey, one was longer by 2 to 1. And when you have one side longer than 2 to 1, then it starts to behave like a one-way slab as opposed to a two-way. And you can actually do the model that way. Right, so that's the beginning of this. So let's redo this a little bit and do another rectangle. You can do it the same size if you want, it doesn't matter. But get at least one side longer than the other by about a ratio of 1.5 to 1, that 3 to 2 ratio. Just 30/20. And what you'll do is, for this tributary modeling, is you're going to draw little lines that represent then the boundary of the load of the tributary area. And you go out at a 45-degree angle. And you do that from the corners. And then between those corners, you draw another line. So what that looks like is one of these hip roofs, right? Here's the big flat section of the roof. There's the other section, and there's the end where it's also then, chamfered over. And that defines your tributary area to each of the edge beams. So we'll take a 1-foot strip here, and we'll take it over to this edge beam. And we'll assume that it's a simply supported beam for now. And we're going to have some sort of uniform load that happens over that region. And then that strip gets linearly smaller in its length, right? And so we'll have a linear variation. We're assuming uniform pressure over that whole area. And that will be the shape of the loading diagram that we'll deal with. We still need to get the intensity, but that'll be the shape on that one. On the one that's on the edge, now I'm just going to turn my page 90 degrees because it'll be easier to draw. If I do that, then you end up with something similar. But this time, it's not a trapezoid. It just comes to the peak. And again, I don't know the magnitude, but I know the basic shape. And it's the same kind of thing here. You've got this little 1-foot strip that's coming along, and we'll go get that peak intensity in here in just a moment. So that's going to be your two basic structural models. That's what it's going to look like. Now let's put some numbers on this thing. This is the 20-foot side. So that's the short edge beam. And then the long one is 30-foot span. So we almost got everything. All we need now are the actual numbers. Now, if you go look up in the live load tables, what you'll find out is that the basic flat roof unreduced live load is 20 pounds per square foot. Sorry, it's off screen there. Right? That's a lot less than the basic live load in an office space. By the way, schools are differentiated from office buildings. If we were on campus right now, that would not be a school building, right? Schools mean K through 12, well, pre-K through 12, right? And I hate to tell you this, You guys are already too old. You are basically the same age as I am. You're like, no, no, I'm not. But in terms of the building code, the consequence of, from a public perception standpoint, the consequence of your fatality and my fatality is equal. But if you are in a school building, K through 12, the emotional trauma of a child being killed in a structural collapse is much higher. And so we actually elevate the loads that we use in a school building, the K through 12. We would be regarded on campus as basically an office building that had assembly areas. And there's also something called the importance factor. So not only do we have nominal or unfactored loads that we use that are higher in school buildings for the live loads, but we also then put it into a higher importance category, and they get elevated even beyond that. So there's a greater level of protection in the schools. That's also why we like to use schools, if they're designed properly, as emergency centers. Not only do they have large spaces, but they also have been designed to resist higher levels of load, so therefore a higher level of hazard. All right, so back to this, 20 pounds per square foot, that's pretty light because you don't generally have parties on roofs. Well, actually you do, right? I mean, if you got access to it, people like to go out and have parties on roofs. Or you go to a restaurant and they have a rooftop bar. Well, you got to design it for a higher level of load than 20 PSF. In that case, that would be a special use that you'd have to deal with. The live load that we're talking about here are temporary placement of roofing materials, temporary placement of equipment or people up there because we oftentimes have rooftop mechanical units that we have to service. That's the kind of live load kind of thing that we're dealing with here, and why it's so much smaller. All right, so there's your value. Now let's get some dimensions here. If this is 45 degrees, then it turns out to be pretty easy, right? Because that distance here and that distance there have to be exactly how much?
10 feet.
Okay. So you use the little triangle to figure out what that's going to be. So what does that mean about that distance from here to here? What does that have to be?
Also 10 feet.
Yep. Why? The easy answer is
It's a 45 degree triangle.
45 degrees, which means that the leftover, now I put the 30 foot in a bad spot here. The leftover space then has to be 10 foot so that the overall is 30 foot, right? And so, I didn't do a great job of getting this perfectly to scale, because that means that we've got each one of these should have equal widths at 10 feet. But, this middle 10 feet is whatever is left over after you do the 45 degrees. And then this tributary load magnitude here, the load magnitude, the W, is then that peak W here is just going to be equal to our pressure times our tributary width. Our tributary width is that 10 foot right there. And so that's our 20 PSF times our 10 foot. And that would be pounds over feet times feet. So we're going to get pounds. That's 200 pounds. But remember this goofy thing that this is per 1 foot strip. So technically you would actually, from a unit standpoint, be dividing by 1 foot. And that gets us back to a distributed load intensity of the 200 pounds per foot. I know that's goofy and weird, but that's how that would work. Now, because of the 45 degree wedge, and we this magnitude here on the straight triangular load is going to be the same one, right? Because that's going to be also 10 foot, and it's the same pressure. So we're going to get the same magnitude for both of those. And I can't see how that would ever change. That would be typical all the way. So that's how you deal with two-way slabs. Again, if you get if this number were 50 compared to 20, I would treat this as a one-way slab because 50 compared to 2 is greater than the 2-to-1 ratio. And I wouldn't dump necessarily any load out here. I would just do a straight uniform all the way across, and I would just design the beam that way. And I don't really need at that point an edge beam on the short direction. Now, the thing is that that's not the way it's going to function. If you build it this way, it's going to behave as a two-way slab. But getting rid of that little triangle on this edge, what a gigantic pain. I'm going to estimate the actual maximum moment as though I have the load all the way across, because this little load here doesn't really do a lot to increase the maximum moment. And I know the moment for the straight uniform is WL squared over 8. And bam, boom, simple, easy. I know immediately what I'm going to design. Okay, I've designed it for a little extra maximum moment. And I got to be careful here, right? I got to be careful that I don't keep running a lot of extras and end up with a beam twice as big as I need to have it. But I'll do that as my initial guess, and then I'll let maybe the computer model refine things. Because one of the things that's generally true is I can't build a computer model unless I know the size of the member. But I don't know the size of the member until I do all the analysis, chicken and egg, right? So you have to guess at something and to get it started. And there are some more sophisticated and expensive programs that will allow you to do a basic schematic, and it will do that iteration for you. And as time goes on, we'll get more and more of that sophistication into the things. But then you're stuck with, well, how do I know that thing was right? Because here's the deal. It don't matter whether the computer model is right or wrong. What matters is what you have told the world to do. The world don't care that the software person got it wrong. You sign and seal this document, it is yours. You get to own it. And so if you stay with the standard of practice, you will be generally safe and you'll be protected. You're not only going to be protected legally, but you'll also be generally safe in doing the right thing. So in other words, there's a lot riding on you. At the same time, that's why we go and do things the way we do, and we'll talk in 2 weeks about the likelihood, the estimated likelihoods of something bad happening in how you handle it. Now, a lot of people run scared on these things, so they say, I don't want to have anything bad happen. I'm not going to use 20 PSF. I'm going to use 40 PSF, and I'll just protect myself. No, because you have more than one responsibility here. Yes, life safety is your job number one, but life safety in terms of the business's life matters too. And if you get a reputation that you are designing things twice as expensive as everybody else, you're not going to get very many jobs and your business is done. So you can't just do one-dimensional thinking here. You got to do multi-dimensional thinking. And it's not just about dollars of construction. There's a lot of factors to begin to think about. And so that's why we start talking about holistic design or systems level design. And eventually you'll learn about the ISI Envision model. If you have already taken the sustainability class, you will have had a basic introduction to that too, because it does matter how much material that we use. We don't want to overuse. So we'll get into all that kind of thing even more later on as we in this module. I keep referring to what happens in 2 weeks, because next week, this is Wednesday, right? Yeah. Next week, we talk about lateral loads and a mouthful, the lateral force resisting system, the LFRS. Lawyers hate that phrase. I've been an expert witness and he couldn't stand it. And then we kept using this phrase because the jury ain't going to like that phrase. It's like, yeah, I understand, but that's what it is. It's the system that we use to resist the lateral force effects. And everything in the particular lawsuit was about that the designers of the system had not accounted for the lateral earth pressures and the way that the soil was going to push on the side of the house. And it racked over and there was hundreds of thousands of dollars of damage. It was amazing. So we're going to get into these systems next week. and we'll be using these tributary area concepts, but we'll be elevating them. And the pun is intended, but we'll be doing a lot more with that kind of model. So that's a key thing that you ask questions this week as you get to trying to head off on this homework assignment. Is this tributary area kind of concept is crucial. And we'll get into more sophisticated things that are happening next week with those lateral force systems. And then we'll come back to the design context and things. Ezra, what I'm doing with the Zoom meetings is today I tried to chop them up into smaller little segments. I didn't do a great job at that.